Welcome to The Explainer. You ever stop and think about how your computer makes any sense of the absolute storm of raw data flying through a cable? Well, today we're pulling back the curtain on the data link layer. It's the unsung hero that turns all that digital noise into the clear, reliable communication we just expect to work every single day.
I mean, seriously, look at this. To a computer, the signal on a wire is just this, an endless, chaotic mess of ones and zeros. There are no spaces, no paragraphs, just pure digital static. So the very first job of the data link layer is to step in and bring some serious order to all that chaos.
And how does it do that? Well, the solution is a process called framing. This is step one in taming the chaos, and it's all about grouping those bits into manageable chunks that we can actually work with.
So a frame is basically the fundamental package for our data. You can think of it like putting individual letters into an envelope. That simple act creates a clear beginning and a clear end, and it turns that endless stream of bits into a nice, orderly series of distinct messages.
Okay, but this brings up a really tricky question. If we use a special pattern of bits to say, hey, this is the end of the frame, what happens if that exact same pattern shows up inside our actual data? The receiver would get confused and just end the frame way too early. So how do we solve that? Well, there's a pretty clever technique for this.
The solution is just so elegant. It's called bit stuffing. The sender ensures that the unique flag pattern, which has 6 ones in a row, can never appear in the actual data. How? It just stuffs an extra 0 after every 5 consecutive ones it finds. So the flag pattern can only show up where it's supposed to, at the start and end of a frame. The receiver then just reverses the process. It's a simple little trick with a really powerful result.
Okay, so we've got our frames, they're all nicely packaged up. But as they travel across a real, physical wire, they run into noise and interference. Bits can get flipped. So now we have a whole new problem. How do we make sure the data inside these frames is actually accurate and hasn't been corrupted on its journey?
And this isn't an exaggeration. A single, tiny flipped bit can have disastrous consequences. It can alter financial data, change a command, or just completely corrupt a file. That's why having a robust way to detect errors isn't just some nice-to-have feature. It is an absolute necessity. Some of the early methods, like parity, were a pretty good start, but, they had their limits. Simple parity, for example, could be completely fooled if 2 bits flipped instead of 1. 2D parity was a big improvement for sure, but modern high-speed networks really demanded something even more foolproof.
And that brings us to the Cyclic Redundancy Check, or CRC. This is the undisputed heavyweight champion of error detection. You'll find it in Ethernet and Wi-Fi pretty much everywhere. And the reason is that it's just incredibly good at catching not only those single-bit errors, but also burst errors, where a whole chunk of data gets scrambled, which, let's be honest, is way more common in the real world.
The way it works is kind of like long division, but with binary numbers. The sender treats the data like one giant number and divides it by a pre-agreed-upon value. The remainder from that division becomes the CRC checksum. Then the receiver does the exact same math. If the remainder on their end is 0, the data is almost certainly perfect. If not, the whole frame gets tossed out. The magic is all in the math. It's specifically designed to be super sensitive to those common burst errors.
Now, to really get a feel for the power of error correction, we have to talk about something called Hamming distance. It's a simple but really powerful idea. How many bits would you have to flip to turn one valid code into another valid code? The bigger that distance, the more resilient our data is to errors.
So here's the rule of thumb. To be able to detect D number of errors, the minimum Hamming distance between any 2 of our valid codes has to be at least D plus 1. This basically creates a buffer zone. So if our only valid codes were 000 and 111, which have a distance of 3, a single bit error like 001 is super easy to spot because, well, it's not a valid code.
But what if we want to do more than just detect an error? What if we want to actually correct it on the fly? Well, for that, we need an even bigger buffer zone. The Hamming distance has to be at least 2D plus 1. So, with our codes 000 and 111, if we receive 001, we can do more than just flag an error. We know it's only 1 bit flip away from 000, but it's 2 flips away from 111, so we can be pretty darn confident in correcting it back to 000.
All right, so now we have well-defined, error-checked frames. Awesome. But in most networks, you've got multiple devices trying to share a single communication line. Think one Ethernet cable or a Wi-Fi channel. So how do we stop them from all talking at once and creating a mess of collisions? Well, that's the job of the Medium Access Control Sublayer, or MAC.
This slide really shows how one simple rule can make a world of difference. With pure ALOHA, devices just transmit whenever they feel like it, which, as you can imagine, leads to total chaos. Slotted ALOHA introduces one tiny rule. You can only start transmitting at the beginning of a specific time slot. That simple change cuts the risk of a collision in half and literally doubles the network's maximum efficiency.
So this shows two classic philosophies for solving this problem. On one hand, you have CSMA/CD, which is what classic Ethernet used. It's kind of optimistic, maybe a little chaotic. Everyone listens, and if it's quiet, they talk. If two talk at once, they both apologize, wait a random amount of time, and try again. It's super fast when things are quiet. On the other hand, you have token passing. This is way more orderly. Think of it like a talking stick. You can't say a word unless you're holding the special token. It's very predictable and there are no collisions, but it can be a little inefficient if only one device has something to say.
All right, enough theory. Let's connect these concepts to something really tangible. We've talked about CSMA/CD and how it needs to detect collisions. It turns out that the actual physics of the network, like the length of the cable and the speed of electricity, imposes some very specific rules on the digital side. Let's solve a classic problem to see exactly how.
Now, I know, this might look like a homework problem, but trust me, the answer to this is fundamental to why Ethernet is built the way it is. The minimum size of an Ethernet frame isn't some random number. It's a direct consequence of the speed of light and the length of the cable.
First things first, we have to figure out the worst-case travel time. We calculate what's called the propagation time. That's how long it takes for the very first bit of a frame to travel from one end of this huge 4-kilometer cable all the way to the other. And in this case, that's 20 microseconds. Now, here is the absolute key to making this work. A station has to keep transmitting long enough for it to hear back about a collision that happens at the farthest possible point on the wire. The worst case is that a collision happens just as its signal arrives at the far end. The news of that collision then has to travel all the way back. That round trip takes twice the propagation time, which is 40 microseconds.
And this is where physics meets protocol. It's so cool. If a station must transmit for at least 40 microseconds on a 10 megabit per second network, we can just do the math to figure out the smallest possible frame. And the result is 400 bits. This is exactly why Ethernet has a minimum frame size. It's a direct result of the physics of the network itself. So let's just recap for a second. We've seen how the data link layer takes this raw, chaotic stream of bits and gives it structure through framing. Then it ensures the data is actually correct with powerful error detection like CRC. And finally, it manages the whole sharing is caring problem on the wire through medium access control. It really does tame the chaos of the physical wire.
But there's a catch. The data link layer is all about getting a frame from one node to its immediate neighbor, one hop. The internet isn't just one hop, right? It's a massive, global network of networks. So how in the world do we find a path across all those different hops to get data from here to the other side of the planet? Well, that question leads us directly to the next layer in our journey, the network layer. And that is a topic for another explainer.